Good morning, everyone. Can you hear me? Good, okay, excellent. Thank you for coming. It's great to be here to tell you about an ongoing research project that we've been doing together with the CERT group at the SEI, and Ed Schwartz is here, our collaborator. Thank you very much. This is not work that I have done, but work that has resulted from this amazing collaboration. There's a few students, Jeremy and Pangchang and Alan, that have been helping us. There's Miltos Alamanis, who's at Microsoft Research, and our colleagues on campus, Claire Lequest and Graham Newbig. So this couldn't have been possible without them. I want to talk to you a little bit today about some research we've been doing to improve the lives of reverse engineers as little as we can, or as much as we can. You probably know already why we might want to do this. One type of application is probably very obvious to people in this room, sort of trying to look at these binaries that are coming, who knows from where, and trying to understand whether they're malicious or not. But there's also reverse engineering of legacy systems that's useful for a number of reasons. Maybe the people that develop these systems aren't around anymore. Maybe the source code isn't around anymore. But you might still want to do something useful with these systems. Banks are using these, and so on. And people have been using all kinds of tools to do this. Some of them are not very user-friendly, as you can see. They require looking at assembly code by engineers, and that's arguably not very user-friendly. Things have gotten better with the advance of these tools, and there's entire tool suites like IDAPro and Hexrace, and more recently Ghidra, that are helping people do this, trying to make these binaries, reverse engineer binaries, more legible, more readable. And here I'm showing you a screenshot from a decompiler, from the Hexrace decompiler specifically. And you could see that the output of these decompilers is something that sort of looks like source code, and it's much more readable for engineers. However, a big problem if you are looking at this example, you will notice it very quickly, is that decompilers are typically unable to assign meaningful names to any of these variables. That's because typically all of this naming information gets lost during compilation, so there's no information about what the original names may have been in these binaries that people are trying to reverse engineer, and therefore there's no information available in these outputs of these decompilers. So we're trying to help improve the situation a little bit. So I'm going to show you today some early results from this research project where we're trying to take decompiler output that looks like this without any meaningful names and automatically refactor it to make it more readable. So you could see how we're trying to rename these variables to something that makes sense in the given context, that carries some meaning with it, rather than just the placeholders that are the default output of these tools. So the results we have are pretty encouraging. We've done some tests on open source code that we pulled from GitHub. I'll tell you all about this later in the rest of my talk. They're pretty encouraging, so we can get a lot of these original names back using probabilistic approaches, and I'll show you how. Okay, so why does this work? So a little bit of the intuition first. The key principle that makes this entire type of research, not just our project, but this research in general, is called the naturalness of software. And this is something that comes out of the University of California, Davis in 2011. There was a very influential paper published at the International Conference on Software Engineering by Hindle et al., illustrating this principle. So what is the principle? So the principle is the following. If you think about natural languages, the kinds of languages that we speak as humans, they can be very complex. For example, you could imagine referring to a tiger in very poetic ways. But actually, typically what happens, most natural utterances that we speak and write day to day tend to be very simple and very repetitive. And there's arguably evolutionary advantages to using such simple and repetitive communication. So while in the hands of masters, poets, writers, and so on, language can be very rich and very complex and very expressive and very powerful. Actually, in nature, day to day, most of this communication is simple and repetitive and boring. Okay, the kind that we speak day to day, which means that it can be captured quite precisely by statistical models. And you've seen tons and tons of applications. I'm sure you're familiar with all of these. They're in your phones and your laptops and so on, that process language to do something useful with. So this is the analogy here, and this is the principle of the naturalness of software. It turns out that similarly, while programming languages and source code can be very complex and very expressive and very powerful, natural programs, the kinds of programs that people write over and over again, are simple and repetitive. And this fact, too, can be exploited, can be put to good use. So 2 examples of this. So I'm going to try to play an audio. Let's see if this works. Imagine a speech recognizer system for natural language. Let's see.
Today, the chairman of the European Central Bank announced that interest rates will remain unchanged.
Can you turn up the volume a little bit? I'm going to play this again.
In Brussels today, the chairman of the European Central Bank announced that interest rates will remain unchanged.
What is the garbled word that's missing there? Is it the fish? What is it? What do you think it is? Bank. Okay, so why did you all think it was bank? Because it sort of fits in the context. So here's another example.
For I equals 0, semicolon, I less than 10, semicolon, plus plus.
Okay, I'm going to play this again just to make sure.
For I equals 0, semicolon, I less than 10, semicolon, plus plus.
What is the missing word there? I, okay? So this is exactly the point. The point is that language is, natural language is very repetitive given context, and so is source code. So are programs written by human engineers. So this is another early result from Gable and Su from 2010. They were showing, using some experiments on open source software, just how repetitive software is, source code is. So I'm showing here on the x-axis the length of code fragments, number of tokens, number of consecutive tokens in code fragments pulled from open source software. And on the y-axis, I'm showing you what fraction of those occur elsewhere in this corpus. And you can see that even up to 20 consecutive tokens, which is arguably a long sequence of code, even at that length, over 70% of these code fragments occur somewhere else, have been seen before. And there's also high redundancy when looking at the absolute exact tokens without doing any sort of normalization and so on. So even at sort of 6 consecutive tokens, those occur about 70% of the time, have been seen elsewhere. So software is really repetitive. So how can we use this? Okay, how can we use the fact that software is so repetitive? And that's what we've been working on. Remember, we're trying to solve this problem. We're trying to do this automatic refactoring of decompiler output from something that doesn't have any meaningful names to something that does. So the idea here is, we could learn variable names in a given context from examples, from many, many examples. If we've seen enough examples, maybe we can just learn what natural names are given that specific context. And if software is really repetitive, then probably so are names. Probably names are also very repetitive in a given context from many examples. So that's what we're doing. So for example, here, if you see a fragment of code like this, probably it's not going to be banana, right, that the developer wrote in that source code. It's probably going to be something like argc. Okay? So this is the idea. So how can we implement this idea? Well, turns out that we are in a very fortunate position of being able to generate arbitrarily many such examples. Why is that? That's because we have access to all of this open source code that's sitting on GitHub and elsewhere. Okay, so given all of this open source code and tools like compilers and decompilers, we could automatically generate, and obviously enough time to wait for all of this to run, we could automatically generate lots and lots of training examples where we have both the original source code with meaningful names, as well as the output of these decompilers, because we could run these decompilers ourselves on programs compiled from the source code, okay? And we could generate arbitrarily many of these. Well, given the limit is how much open source code we can get our hands on. Okay, so I'm going to tell you a couple of challenges to actually doing this, but this was the key idea of our work. So the first part is generating these examples. It's not quite as straightforward as I made it seem. If you're interested in all the technical details, there's a paper coming out in a couple of weeks at the Conference on Automated Software Engineering where you can find all of this. It's out on the web. You can find it, or just ask me later. OK, so why is this not straightforward? Well, for one example is that one reason is that decompilers change the structure of the programs that are being compiled and then decompiled. For example, there's different arguments in the output of the decompilers compared to the original source code of these programs. There's different numbers of variables. Sometimes the decompilers cannot figure out exactly what the original variables were, and there's some mismatch between those. There's even different kinds of loops. You'll see how while loops, perhaps, that have been written by humans turn into for loops and so on. So all kinds of changes make these programs different, so the source and the target different. So in order to do this, to actually be able to do any kind of learning probabilistically from these examples, we need a way to calculate the alignment between these two. Okay? And the idea here is that the DWARF, the debug information that is possible to embed into these binaries carries all this information with it, and we can exploit that. So here I'm showing you two examples, two different loops written in C, very simple loops. One uses a for construct, and the other one uses a while construct. And turns out because of how compilers work, these two programs that are otherwise different compile to the same assembly code. Okay? And you could try this out yourselves if you don't believe me. So here, the key idea, the key insight that we have is that, in this DWARF debug information that we can embed in the binaries, because we are the ones compiling these programs to begin with, remember, the operations on variables and their offsets remain the same. So you'll see this is an excerpt from an abstract syntax tree from these programs, and you will see how all of these memory offsets in both the source and the target remain the same. And this is exactly what allows us to align, to calculate this alignment between the original names that perhaps human developers wrote and these names that are produced, these placeholder names produced by the decompilers. OK, so this was part one. How do we generate lots and lots of training examples? And we do it in this way. Part two is, how can we learn from these examples? Can we do anything interesting here? So we've built a tool called DIRE. We call this the Decompiled Identifier Renaming Engine. And you can find, again, all the technical details in the same paper I mentioned earlier that uses machine learning to learn these probabilistic mappings between variable names. So remember, names are repetitive in a given context. This was the whole reason why this research works. So the question here becomes, how do we capture this context? We know that names are repetitive in a given context, but how do we capture this context? And we do this in a number of ways. I'll give you some examples. So just to walk through this, a running example, here's a small, simple program that copies, I guess, the contents of a string into another one. So context could be lexical. Here, I'm showing you how, by simply tokenizing this program, I obtain the sequence of tokens. And just looking back or looking forward, I could capture context from this sequence of tokens lexically. It could be as simple as that. Or context could be syntactic, could be structural, because programs are not just a sequence of lexical tokens. They're also a syntax tree. They carry meaning with them, and they have syntax and structure and so on. So the question is, how do we encode and embed this context? So we've built this neural network model to do this. We're using an encoder-decoder architecture. This is pretty standard for machine translation and natural language processing. The idea is that the encoder reads in the input and generates a sequence of a vector of real numbers, and then the decoder takes these vectors of real numbers and generates the output. This is pretty standard as far as the architecture goes, but we're innovating in the implementation of this architecture. For encoding, we're using two things. We're using a lexical encoder that reads in sequences of tokens in the same way I showed you a slide ago or two. and converts this into a vector of real numbers. Couple of interesting things here, and you can, again, find all the details in the paper or talk to me offline. One interesting thing is we are sub-tokenizing names, and we're doing this probabilistically in an interesting way. And this helps a lot with reducing the vocabulary size and helps a lot with training time. And then we're able to reconstruct names from these different subtokens, from these different parts. Another interesting thing is we are looking both back as well as forward in the sequence of tokens for context. Okay, so if you think about it, maybe the usage of a variable that is defined somewhere above in the program, the usage of the variable carries a lot of information about what the name of that variable should be. So it's also useful to look forward in a program, not just backwards, which is an intuitive way. And then we're doing also something with the abstract syntax trees of these programs to encode more of the structure. And some key interesting things here. For example, in the abstract syntax tree, we are creating additional links or edges between uses of the same variable. Okay, so if you think about how programs are laid out, typically top to bottom and so on, and they're read sequentially, there could be sequentially in this lexical list of tokens, very large distance between when a variable is defined and when it's used. So if I only look at this lexically, I might be so far ahead or behind that I lose all of this context information if my window is not long enough, large enough. So here we're trying to take shortcuts to connect together definitions of variables and all of their uses so that we can learn from all of this local context that's around where variables are defined and used. Similarly, we're linking together in these trees the nodes that belong to these variables to the definition of these functions. That also carries a lot of information as to what the names are, and so on. We have some more tricks that we're applying to these abstract syntax trees that I'm happy to talk to you about offline. So given these encodings, we generate some unified encoding for each variable name to represent all the different variables in our programs. And we're doing the same thing for all the other code elements in the program, the language constructs and so on. And we're feeding this into a decoder. Now, the decoder starts doing this, as I mentioned, at subtoken level, starts generating names. So here, for example, we start generating the first name, and we're using something called attention. This is a deep learning model. I could talk to you about this, again, separately offline. We're using attention to guide the model as to during this generation phase. So here you could see how we start generating names for variables. Perhaps at the first step, we generate something called destination. We haven't hit a stop token yet, so we keep generating. This way, we maybe generate a second additional part of this same name, address, or ADDR. So the name would become this address here. And maybe then we hit a stop token and so on, and we keep doing this for other variables in our program. Okay, one subtoken at a time. So this is basically the idea. So now you could be asking, how well does this work? Does it do anything? And it's pretty hard to actually answer this question because we really don't have good ground truth data. We don't know what it means for a name to be really good or really bad. But what we can do is approximate this a little bit. So here we're making the assumption that the original, presumably human-written names in these open source programs that we're finding on GitHub and elsewhere, that these names are good. We're assuming that. And the question becomes, therefore, how many of these original names can we recover, if any? So we've done some experiments. We looked at about 160,000 unique x86 or 64 binaries. We have about 1.2 million decompiled functions that we've looked at, and we've split this set into test and training and validation, typical for machine learning problems. And here's how well we're doing. I've broken this. So this is the percentage of original names in these programs that we're able to recover. I have I'm showing you here both the output of the purely lexical model that uses the lexical encoder, or a purely structural model that uses only the structural encoder, the one based on the abstract syntax tree, as well as the combination, which we call DWARF. And you can see that the combination here of lexical and syntactic information performs the best, but really just the lexical model gets you a lot of the way there. And we're getting about 74% of these original names. We're able to recover them exactly. You might be wondering, does it matter how much data you've seen? The answer is yes. So here on the x-axis, I'm showing you fractions of this training data set that I've mentioned a minute ago. And on the y-axis, I'm showing you the accuracy of our model. The far right point is the final accuracy, 74%. And I'm showing you how by training on smaller and smaller subsets of our training data, we're also losing accuracy this way, as you would expect. So this also shows, by the way, promise that by training on more and more data, we could be doing even better. Does it matter if we've seen these code fragments before? Again, as you would expect, the answer is yes. So here what we've done is we have made sure that none of the functions that we see in our training occur in our test set, which is maybe most closely aligned with a malicious attacker scenario that you could imagine. And we're seeing that the accuracy is typically lower when we're doing this. And it's typically higher when we've seen more of these examples in the training set, which is more typical of a sort of legacy system reverse engineering scenario. Finally, an example. So just to give you a flavor for what this looks like, here's a piece of code from our corpus. I'm showing you 3 columns in the table there on the right-hand side. The developer column are the original names given by the author of this piece of code for V1, V2, and V3, the placeholders produced by the Decompiler. And I'm showing you also the names produced by the 3 models that we tested, the purely lexical one, the purely structural one, and the combination of the 2. So for example, you could see how we are guessing accurately the 2 of the 3 names here. We're guessing file name, and we're guessing mode accurately, which were the original names given by the author of this piece of code. And we're failing on the 3rd variable there. So there's still a lot of room for improvement. OK, so just to summarize, I talked about how compilation loses a lot of information. And this makes the life of reverse engineers harder when they're looking at reverse engineer binaries. In particular, I talked about this problem of renaming variables or variable names in Decompiler output, which are only placeholders, typically. And I've shown you a machine learning-based approach using deep learning that tries to recover as many of these names as possible. I'm on campus. My name is Bogdan Vasilescu again. And together with my students, we're the Strudel Lab. And I'm happy to talk to you more about any of this. Thank you.
We have time for one quick question. Does anybody have a question they'd like to ask? You did a great job shouting it out loud. Go ahead.
I can hear you.
I sort of had the feeling that you sort of rely on a few sort of critical aspects like the decompiler, the DWARF sort of debugging symbols, the notion that somehow the AST, to find that sort of offset between the actual code versus one that is reconstructed by a decompiler, you rely on the similarity in the sense that the assembly language or the AST sort of at the ground level is somehow similar. However, if you really look at how things work in practice, at least a majority of the code that comes out in binary, some of them or most of them lack the DWARF debugging symbols. They are packed, which means there's another layer like UPX or ASPAC or VM Protect that's added on top of the binary to reduce its size. And this is even true for malicious code because they really don't want you to decompile it. So they have anti-decompiler techniques that they embed in their code. So I guess, and the last point with the assembly language, and I'm sure you know this, if you take two compilers and feed the same C source code to those two compilers, like GCC and Clang, they're going to produce different assembly language code. So how crucial are these sort of foundational assumptions that you are making to this process? I mean, have you guys thought about this, evaluated this? I would be, curious to hear your thoughts.
Yeah, thanks. That's a great question. It's probably 10 questions, not one. So I'm not sure I'll be able to answer all of your questions in this one short answer, but I will give you one short answer. There's nothing in the sort of usage scenario for this technology that we're building. There's nothing here that assumes that, for example, debug symbols are present in the binaries and things like that. We're only doing this for training purposes. Okay? And once we've trained a model, the model can be used out of the box on anything. So now, the key idea that I mentioned earlier is this ability of generating arbitrary amounts of training data. So for many of the things you mentioned in your comment, different compilers, different optimizations, and so on, we could similarly generate training data to match those settings. Does that make sense? So as long as we're able to simulate these settings that you're referring to that actual practitioners would encounter in their actual work, as long as we're able to simulate those during training time, we hope that we could do pretty well on these. Thank you.